You want to go around and do intros, guys? Say what you've been working on?
Sure.
Yeah. Zach, when you start.
Zach Buttonweezer. I've been working on a remote control car that's controlled with using only accelerometers and gyros.
Hi, I'm Andrew Millick, and I am working on a similar car, but it doesn't really have any control, and it goes to a GPS location.
Hi, I'm Akil Vaswani. I'm working on controlling a wireless weather station, so I can get the weather outside instantaneously.
Hi, I'm David Dalal. I'm working on a real-time digital stethoscope. Mm-hmm.
Hi, I'm Farhana Chaudhry. I'm working on the wind lantern. The new design.
I'm Sam Fishman, and I'm working on a stoplight that you control over Wi-Fi.
I'm Donna Zahn, and I've been working on a Geiger counter that transmits data to a computer and tracks it.
I'm Chris. I'm working on a 3D LED cube that I can control with a joystick and push buttons. I'm going to program like Snake, but in 3D and do some cool animation.
I'm Andrew. I'm working on a wireless power.
Okay, so how's everyone? Has everything you tried to do in your project gone perfectly the first time you tried it? Awesome. So you guys are all engineers. You know it. So I want to tell you a little bit about, give you kind of a long introduction of myself and kind of go through steps of my career so you can see what's been like for me to become an engineer and hopefully inspire you guys to kind of keep up pursuing engineering and entrepreneurship as you keep going along. So I went to college. How many of you guys want to go to college? Great first step. Great first step. Anyone think they want to major in engineering? Maybe.
Possibly.
Not really sure what engineering can do for you, not sure what engineers do, so hopefully I can clear some of that up. Engineers do tons and tons of stuff. I'm just one type of engineer. So I went to college at Carnegie Mellon University in Pittsburgh for mechanical and biomedical engineering and minored in robotics and business, which means that I still didn't know what I wanted to do, and I took as many classes as I could. And it was a great time. I highly recommend it. And then I went to a master's program in University of Delaware in biomechanics and movement science. Because after playing with some robotics projects and stuff like that in college and in high school, I got really interested in how our body decides to move stuff. Like, we don't need a GPS locator to get us from this corner to that corner. I know how to get there without being given coordinates. I can close my eyes and I can touch this computer screen. I don't have any accelerometers or gyroscopes or potentiometers in my elbow, and I can still do that. So I got really interested in how the parallels between mechanical engineering and biomechanics and how our body work. And then I got a job at Honeybee Robotics right here in Manhattan, making robots that go to Mars. So I want to show you a few minutes of this clip that I'll talk through.
When people look at it, it looks crazy. That's a very natural thing.
We know there's a couple of robots on Mars right now.
Sometimes when we look at it.
Yeah. Do you know what their names are?
It is the
Spirit and
result
Opportunity.
of
They're
reason.
two little rovers that have robotic cars basically that have arms at the end of them that can drill into and take pictures of rocks.
The top
Right
of the
now, there's a much
down
bigger
to
one
the surface.
that's the size of a bumper car.
It takes us 7 minutes.
And it's going to land in
It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away.
It was supposed to launch in 2009, and it didn't. It launched
So
in 2011.
when we first get word that we've touched the top of the atmosphere, the vehicle has been alive and dead on the surface for at least 7 minutes.
Entry, descent, and landing, also known as the drift bridge and 7 minutes of terror, because
We've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0 in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself. If any one thing doesn't work just right, it's game over.
We
slam into the atmosphere and develop so much aerodynamic drag, our it heats up and it glows like the surface of the sun. 1,600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow constraint. This is one of the biggest challenges that we're facing, and one that we have never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
The parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck-snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we've got, it will only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we've got to cut it off and then come down in rockets. Once we turn those rocket motors on, we don't do something. We're just going to smack right back into the parachute. So the first thing we do is make this really radical divert. We fly off to the sun. Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land. And we head straight down to the bottom of the crater, right beside a 6-kilometer high mountain.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover. It could damage mechanisms and it could damage instruments. So the way we solve that problem is by using the Skytrain maneuver.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long, and then gently deposit it on its wheels, on the surface.
As the rover touches down and is now on the ground, the descent stage is in a collision course with the rover. We must cut the bridle immediately and fly the descent stage to a safe distance from the rover.
Every time we get a robot on Mars, we create a lot of space garbage. So with this, the robot system that I worked on will do is the sample manipulation system that I helped build is this little thing that's like maybe 11 inches by 6 inches that has 40 different little sample cups in it that takes dirt from Mars with a scoop throws it into it and then rotates it to different science instruments and then can push up on the sample cup with a force of about 300 pounds to create a seal. And it has to seal with these science instruments that basically bake the dirt at 1100 degrees Celsius, which is really, really, really hot, and see what comes out of the dirt, basically. So if there's the right elements in the dirt, we think that the soil on Mars could maybe have supported life for quite some time, or maybe still does. So that was a really, really great first job, and it's also really, really challenging because when you guys do projects here, you get to kind of mess up and try it again, right? If it doesn't work the first time, and you get to go through different iterations, right? Here, they don't like it when you mess up, and you miss Mars, or you crash, Mars, and it's not even really something we're trying to do yet because it's so hard and it's so far away. So we just send robots and cameras and try to get data back from it to learn more about it. So working in the aerospace industry is interesting because nothing you make can fail. It has to work right the first time and every time for the life of the mission. So it's a pretty intense job. After I worked for Honeybee Robotics, I started my own company. It's called Dustyn Roberts, and my full name is Dustyn Roberts. And really, that was because one of my friends said, if the ER in your last name was an O, you'd be Dustyn Roberts. So I checked if that URL was available, and it was. So that was my company name. And I got to work on everything from working with a podiatrist to do clinical gait analysis and look at the biomechanics of human bodies, to working on an infant incubator that will be deployed for use in third world countries, very low cost incubator. And working for yourself can be really stressful, but also really fun too. Like I pick and choose the projects I wanted to work on, and I could, sleep until noon and work until midnight if I wanted to, or I could make my own hours and do my own projects. And one thing that I did when I was working on my own was write a book called Making Things Move. So one of you have probably heard of it because you're doing a project from the book, right? How many of you guys think engineers write a lot? Yeah. Anyone who didn't raise their hand is wrong. Engineers write a lot, and it's actually something I didn't know until after college. In college, I had one required class and one required English class, and the teacher was pretty flexible, so we did a couple of things like make a scrapbook in school instead of writing an essay, and I figured I'd never have to write anything again. That's one of the reasons I chose engineering, and it turns out I was totally dead wrong. From my first job all the way through writing an actual 300-page plus book, we write all the time. Every time you do a project, it's not helpful to your company unless you document it. So you have to write out the steps, you have to write out just like your lab reports. Well, a little more fun than that. To write out the steps, you have to write it out so other people can reproduce it. You have to write it out so the other people in your team can understand what you did. And then ultimately, if you're reporting what you did to NASA or a design client or a doctor, you have to tell them what you did. So you have to make a presentation, or you have to make a report that they can understand in technical terms. So you end up writing a lot, but it's really, really satisfying after having written a lot and writing this book. And then I get emails from, a mom whose 7-year-old wants to make robot cars and had no idea where to start. So they got my book and they picked it up and started reading it. I said, okay. I'm writing, but at least someone's reading it and they're understanding it and they're being inspired by it. So that was fun. And so any chance you have to make your communication skills better will always help you. Even if you don't end up writing a book, even if you don't end up writing your reports for your companies, any chance you have to communicate your ideas helps you professionally and at school. So I highly recommend taking advantage of chances like that. And I put this little picture up on top here because where I wrote this book, I was an artist in residence at IBM Art and Technology Center. And that was the first time I officially, as an engineer, got called an artist. And I thought it was really cool because this place is in West Manhattan. It's on 21st Street. It's basically a huge warehouse, and they have really cool tools like 3D printers and laser cutter. And do you guys have any of that stuff here?
Not exactly, though there is some limited access to it through
solder irons, shop tools, and stuff like that. A couple of drills, probably. So it was great to be able to write a book like this at a place that had tools for me to use. So I could think of something and go downstairs and print it, or I could think of something and laser cut it. And that was a really fun place that supports engineers and artists. So I got to think about and learn from artists, actually, and how their process works, about how when they think of creating something, they may not know all the technical hurdles that we do as engineers, but they kind of do the same process where they try it out, it doesn't work, they try something new, and that doesn't work, they try something new, and eventually they narrow down on what works. And there was a lot of interesting parallels there. So after I finished this book, I went to college again. What grade are you guys in?
Well, we're all in different grades, kind of.
Okay, so freshman through sophomore through senior year of high school, pretty much? Okay, so that's like 9th through 12th grade. I'm in 26th grade right now. I went back to school after 6 years of working to get a PhD, and I didn't know what that was a long time ago when I was in high school. It's basically the degree that all of your professors will have when you're in college, which means they studied for 5 or 6 years after college to learn something hopefully well enough to teach when you're in college. So that's what I'm doing now. I'm a PhD student at NYU Poly, which is right across the river in Brooklyn, and I'm in the mechanical engineering department again. So I get to study, and the cool part about PhDs and graduate school in general is that they pay you to go to school. I get paid to go to school, not even just cover tuition. They pay me a salary to go there and research. And my job all day is working on problems that I think are interesting. So it's really, really great career path for me. It's something I recommend thinking about down the line. So this is a researcher in my field named Max Donelon. And has anyone ever heard of TED? Have you guys seen TED Talks and stuff? Okay. This is a TEDx talk, and he talked about his project on using human energy to generate electricity.
Our lives are
So I
powered,
wanted to show you a couple
has about 100 portables to the grid. And I want to cut that wire. And I want to do so by tapping into your power. Now, you may not have thought about it quite this way, but you guys are an incredible source of portable and reliable electricity. So let's think this through first. So let's begin with the energy that you eat. You guys eat food. Now, it turns out that food, like this granola bar, has about 100 times as much energy per unit mass as batteries. That means you can either bring along a 2-ounce granola bar or a 12-pound lithium-ion battery, okay, in terms of the amount of useful energy that's available. And you store energy in your body as fat. That's the most dense food there is, and that's the way you store it in your body. And the average person is about 15% fat, which makes you roughly equivalent to a 1-ton battery stored in your body.
Think about this. We use, how many people have a cell phone that doesn't, the charge doesn't even last the whole day? Me too. But if we're carrying around this 1-ton worth of energy in our bodies, why is it that our cell phones die? It's kind of silly. One thing, so this is a flashlight that charges when you crank it, right? And this happens because I ate food, I'm eating food now, and I have this energy that I can turn into motion, and motion can generate electricity for us. So we created batteries because humans are really good at doing two things. One is being lazy, and one is being creative. So we can think of ways to charge our phone without actually having to go on crank our phone or go on a stationary bike and crank the batteries for it. We do, it's convenient, right? And that leads to lots of other problems I won't get into in this talk. But there's many ways that we can generate our own electricity without even actually putting a ton of effort into it. And I'll show you what Max Donelon thinks that we should do.
Kicks. It's going to take a little while, a couple kicks to light this light, because there's no battery in here. There's no magic in here.
So he's got a similar flashlight to this, and it's going to make
stand over here a little bit.
knee brace.
See, sure. I don't want to fall over.
This is the same idea. He's using his own body energy to make this flashlight light up. And if instead of directly making the flashlight light up, you stored it in really efficient batteries, then you had the potential
So I've done it a million times. I love it still.
Using the motion that we do for free, walking and running, and using that to charge your batteries. So with this type of understanding of how muscles work, how biomedical engineering works, how product design works, how the hinges in the knee brace work, what materials to make that knee brace out of, the mechanical engineering principles, and all this stuff. So there's lots and lots of different areas of expertise you have to work towards to be able to do something like this. And that's what makes engineering, for me, so interesting, because there's always something new to learn. There's always something new to try. And there's always someone else that you might meet that has a suggestion that you might not have thought of yet. So that's a really long intro to who I am and what I do. And I'm also doing some robotics research too at NYU Poly. And I want to kind of open it up for questions and see what you guys.
It seems like writing a book would take a lot of time and a lot of your energy. So what made you decide to write a book instead of just continuing on the projects you were doing or finding new ones?
Good question. One thing I didn't mention is that I have been teaching for about 6 years at a graduate school program at NYU. And the program is called Interactive Telecommunications Program, and it's basically engineering for artists, a lot of it. And I've been teaching a class on engineering to artists kind of like mechanical engineering 101. A lot of the stuff that you're doing in this class, to people who have never heard of LEDs or soldering irons and things like that. So after about 5 years of teaching the class that I invented, it was called Mechanisms and Things That Move, I had no reference material. So right, when you guys take chemistry or any of your classes, you have a book, and you can look up the answers, and you have a flow of learning what we do. I didn't have that for my class, so after 5 years, one of my colleagues, my boss actually, had written a book called Making Things Talk. It was about networked objects, and you guys have done a little bit of that, it sounds, with GPS and computer connected logic to your robot and stuff. And someone suggested that I write a similar book called Making Things Move. Making Things Talk, Making Things Move, great. So I said, it would really be nice to have reference books so I don't have to only teach this at NYU. I can teach other people that have never met me about this kind of stuff. And it doesn't assume that you know a lot about robotics or Arduino or any of that stuff. It kind of starts from the beginning. So that did take a lot of time. It was my job for 4 or 5 months, almost full time. And now I can teach the class and say, read chapter 2. Instead of saying, check out this video on TED, check out this video here, or read this Wikipedia article, it's nice to have that reference.
You must have other questions.
Like, how does engineering become a career? Like, what does it take to turn like a hobby into a source of income?
That's a great question. There's tons of different kinds of engineers, and you don't have to necessarily even know what kind you want to be when you get into school. So I started mechanical engineering. I started materials engineering actually, and then went into mechanical. And they're similar in a lot of ways. But I have friends that went into civil engineering and now design buildings or design bridges. I have friends that started in engineering and then switched into architecture, which is also very related to engineering, more designing buildings. And mechanical engineering itself is sometimes I've heard called like the liberal arts of engineering because you can do so many things with it.
Yeah.
With a mechanical engineering degree, I could work on robots for Mars, or I could work on the heating system for this building. So as you progress through an engineering degree, there'll be classes at the Career Center at your college that start to introduce you to what kind of careers you can get as an engineer. And if you're thinking of, if you see a company on TV, like one company I think is really cool is called the system is called the Da Vinci Surgical System. It's a robotic surgery tool. So if you hear cool stuff like that, you look it up and say like, oh look, they're hiring engineers, and look at the job descriptions, and you'll say, bachelor's degree in mechanical engineering required, or bachelor's degree in electrical engineering required. So kind of reverse engineering jobs that you think sound cool is a good way to see what engineers end up doing. Yeah. And if the job that you think sounds cool reverse engineers into, a marketing degree or something like that, then you'll know that there's that you can minor in that, or there's other pursuits that interest you.
I see.
Does that help?
Yeah.
I have a question.
Yeah?
You go.
As a female engineer, did you feel like suffer through any hardship or anything in your career?
Not really. I've been really lucky, and if anything, I think it's helped me because when I first started working at Honeywell Robotics, I was the only female engineer there, and one of the guys was saying how they always had a lot of respect for the female engineers in their classes because there'd be like 3 out of 40, and they knew the ones that were there because they were good and they didn't get scared away. So that's always worked for me. And the only time I really got it pointed out to me was when I interviewed for my first job. I was with the chief engineer in a dark room in the basement of Honeywell Robotics, and they said, we don't have a lot of girls here. And like, yeah, I went to an engineering school. There's only 10% of us there, pretty much. I've got a brother. I'm used to it. I think I can handle it. And that was really it. But I don't think it's ever hurt me.
I just want to know why and how did you start your own company, and what's the expertise of your teammates in your team, in your company?
one thing I didn't know about starting a company is that you don't even have to do anything. You can just start today. Like if I said, I've got $50, I want you to build me a robot, you are all of a sudden your own company. There's no weirdness you have to do with like taxes or legal stuff. You can, but it's really simple to start out small like that. And that's what I did. I said, I am my own company. And I had started doing a bunch of part-time jobs and realized that people that did that for a living called themselves consultants. So I started saying I'm an engineering consulting company. And my company has always been just me. And I've worked with some collaborators once in a while, but it's an independent company. So it's registered now as a sole proprietorship in New York, which you don't even need to do. All that means is no one can take my name, which I don't know anyone named Dustyn Roberts anyway, so it's probably not even that useful to have it registered. But yeah, you can kind of just start small, and once you have a business card that says you're a company, people start to take you seriously, and then you can get jobs like that.
When you just got out of your undergraduate degree in mechanical engineering, did you go straight for your master's? And, well, if so, then, I mean, how were the job prospects after that? And if not, then how were the job prospects after that as well?
Yeah, I did go right from undergrad to a one-year master's degree program at University of Delaware. And it was really facilitated by my undergraduate advisor, because I said, I'd just taken one class in biomechanics, and I was really interested in learning more about it. And most of the places hiring people to do stuff in that field, like making knee braces or making sports equipment and stuff, wanted to see in the job requirements online, wanted master's degrees in the area. And I really wanted to spend more time learning about that stuff. So I said, of any good programs that would be right for me. And it turns out at University of Delaware there was a biomechanics program that's halfway between the mechanical engineering department and physical therapy department. So I got to take classes in both. And that worked out perfectly for me. Everyone has their own kind of trajectory, whether grad school was worth it for them or not. And I also got paid to go to grad school, so that was a really easy decision. But I think I did get a job. So it was a job as a research assistant in a lab while I went to school and got to learn more. And then, so I didn't really spend too much time looking for jobs right after undergrad because I got into grad school and I knew I wanted to do that. And then after grad school, it took a few months to find a job in New York. And interviewed at a bunch of different places, but it wasn't that was 2004. It wasn't super hard at that time, and most of my friends that graduated, either from undergrad or master's, had full-time jobs within 3 or 4 months, I'd say, of graduating.
How did you get involved with IBM?
When I worked at Honeybee Robotics, the Mars rover job, there was a couple of graduates from the ITP program at NYU that I now teach at. And before I started teaching there, there was one artist and his wife who had a residency called at IBM, where they basically give you a little bit of money and they give you some desk space. They let you play with the cool tools and make cool projects. So they said, we're making a robotic puppets of ourselves. We need a mechanical engineer to help, because they were not engineers at all. They were artists and didn't know anything about motors or bearings or gears. So I said, sure, I'll try. I barely knew anything at that time either, because I had just finished undergrad. And I hung around IBM with them once or twice a week in the evenings, and we modeled parts to make robotic puppets of them. So we ended up making a knitting robot to represent my friend Michelle. So it was a bunch of 3D printed square ugly looking parts, but they rotated like this. So we put little wooden dowels in the robot's hands, and it looked like, sort of, you use your imagination, that the robot was knitting. So that's how I got involved with IBM. And then a couple years down the road, when it came time to write this book, I was like, look, I really don't want to do all this on the kitchen table. It'd be nice to have some desk space, and applied for residency and was lucky enough to get it.
Other questions? Thanks a lot. So if you guys, maybe Dustyn wants to check out some of your projects if you guys want to start working on them.